Question 9.59. A speedway turn with the radius of curvature r is banked at an angle theta above the horizontal. Part A of the question is asking us what is the optimal speed at which to take the turn if the track surface is iced over, that is, if there is very little friction between the tires and the track. So let us first sketch the problem. When we bank the road, that means we raise the edges of the road by an angle theta with the horizontal. So this is my banked road. Then we place the car on top of the road. We have to identify all the forces acting on this car. So we first draw the force due to gravity, which is acting vertically down, Fg. Then we have the normal force, which is perpendicular to the surface, N. Then we have the force of friction, F, which points towards the center of the curved path. In solved problem 9.4, we discussed the maximum speed with which an object can take a turn along a banked curve. And that speed was given by V equals square root Rg sine theta plus mu s cosine theta over cosine theta minus mu s sine theta. If you want to learn how to arrive at this equation, you can refer to my video of solve problem 9.4, where I have discussed step by step on how to arrive at this rule for velocity. Now, question A is asking us what is the optimal speed with which you can take the turn if the surface is iced over. Iced over means that the force of friction is almost negligible. And if the force of friction is negligible, in this expression for velocity here, I can remove all the terms with the coefficient of static friction. So if I consider these terms with static friction mu s to be 0, or if I remove them, I get the expression for the optimal speed V optimal to be equal to square root Rg sine theta over cosine theta. Now we know that sine theta over cosine theta is equal to tan theta. I will substitute that here. We get V optimal to be equal to square root Rg. In place of sine theta over cosine theta, I will write tan theta. So this is the expression for the optimal speed V with which the car can take the turn safely if the track surface is iced over. Part B of the question is asking you, if the track surface is iced free and there is a coefficient of friction mu s between the tires and the track, what are the maximum and minimum speed at which this turn can be taken? So now you have the force of friction and the coefficient of friction is mu s. The maximum speed with which you can take the turn is the speed that we have here. We already derived this before. This is the maximum speed with which any car can move with in order to safely take a turn around the banked curve. The minimum speed, on the other hand, when you're considering the minimum speed, all you need to do is reverse the sign on every term with coefficient of static friction mu s. Because now in this situation when the speed is minimum, the force of friction acts in opposite direction to prevent the car from slipping down the track. So wherever you have mu s, change the sign in front of the mu s and make it opposite to what is present here. So I will write square root Rg sine theta. In case of plus here, I will write minus mu s cosine theta over cosine theta. In place of minus here, I will write plus mu s sine theta. So these are the expressions of minimum and maximum speed at which the turn can be taken when you have the force of friction. In part C, we have to evaluate the results of part A and B for r equals 400 meter, theta equals 45 degree, and mu s equals 0.700. So we are going to just substitute these values of r, theta, and mu s in the expressions of v we found before. So we get v optimal to be equal to square root rg tan theta. Let's substitute. R is 400, g is 9.81, tan of the angle 45. And when you solve this, you get the optimal speed to be equal to 62.6 meter per second. Then we do the same thing for Vmax. We write square root. R is 400 times G is 9.81. Sine of the angle 45 plus mu s is 0.700. Cosine of the angle 45 divide by cosine 45 minus 0.700 sine 45. And when you solve this, you get the maximum speed to be equal to 149.11 meter per second, which you can just write as 149 meter per second. Then we solve for the minimum speed. We write square root. R is again 400 times 9.8 into sine of the angle 45 minus 0.700 cosine 45 over cosine 45 plus 0.700 sine 45. And then solve, you get V minimum to be equal to 26.31 meter per second. This is how you find the optimal speed, the maximum speed, and the minimum speed. Optimal speed is when you have no force of friction, whereas V max is the maximum speed you can take along the banked curve with the force of friction involved, and V minimum is the minimum speed with the force of friction.